All right, and we are live again. And today we are gonna I spent a lot of time chatting. Let me just switch on the chat. Right. So I've decided what I wanna do already, and it's partly because my eyes kind of hurt. I've been like doing shit. I've been learning React query and making my YouTube clone all day long. That took a long while, more than it should have, honestly. Right, and what I did today is lead code problem of the day. So, and it was easy. I don't know what's happening, but lead code, the platform is somehow obsessed with coming tomorrow. Wait, I don't know, man. What's your budget for tomorrow looking like? Right, as I was saying, lead code, the platform I code on, it's obsessed with Dominoes. Oh, can you guys hear me though? Because my mic was here all this while. I did not put it on. Anyways, like I was saying, the platform is somehow obsessed with Dominoes. So last 3 days I've been like doing problem of the days, and it's all just Dominoes, about Dominoes, like reversing a domino, make the top rows the same. It's just weird. And today I decided that I'm gonna look at a few more not algorithm videos, data structure videos from William Fissett. And maybe we'll do a few questions from here, right? We can do heaps learning problems. These are just four, and it's gonna be pretty fun, I think. So we're gonna do that. I was thinking you can just go to college if you don't wanna join. Yeah, but I don't want to go to college either because my I asked my roommate if he's going and he's just gonna go play cricket somewhere. I don't want to go alone. I will let you down. I will bring you up. Right. And I was watching this video from Theo from t3.gg. It is Tim Cook now. Oh yeah. Oh yeah. Removing elements. I think I've watched this video. Welcome back. Just a second. Let me inserting elements with heaps since this gives them the best complexity. Abstract data type. Heaps are not the only way to implement priority queues. Sorted list. Binary heap, Fibonacci heap, binomial heap. We're gonna use a binary heap, right? Complete binary tree is a tree in which every level except possibly the last is completely filled and all the possible nodes are as far left as possible. Heap representation, the parent, so not coming with us. I can. I'm just confused if I should go or not. I can't convince myself not to go, and I can't convince myself to go. What should I do? And when are you guys leaving exactly? Well, the parent index is what? N, and the children index is 2n plus 1 and 2n plus 2, right? Wait. Oh, I'll wait. Yeah, exactly. Insert. Watch this. This guy is gonna insert 13. And then he's gonna heapify it. This travels up. This travels up. Okay, so this travels up like that. Yes. Choose one, two. I choose two. What's the second? The middle finger. What's the option that I chose? Don't go. Oh God. I'm actually fine with that reality. Removing elements from my array. Sure, won't go then. 4 remove, 12 remove, 3, 4 remove, 6. You replace it and then you sync this. Bubbling down. Now instead of bubbling up, look at children, select the smallest one, swap with the smallest. Select the left node to break tie. Hi, Apeksha. Dude, screen. What about the screen? Oh, I haven't shared the screen, have I? Why do I keep forgetting? I honestly, I did not have it on. You look nice today, do I now? Do you even watch me every day? I don't think you do. My bad, bro, my bad. See, that's the sort of audience I want. Someone that's actually aware of what I should be doing. Right, so he's removing 12. Do we bubble up or down? We already said. Right, do you bubble up or do you bubble down? That's a really nice question. I want to see what he says about this. You do watch me every day. I did not know that. Swear to God, I need to find another way to unmute and mute, bro. And then I need to switch on this. So many things I need to be reminded of. Anyways,
So 5 was smaller, so we swapped it with 5. Now 8 is smaller, so we swapped it with 8. And again, the heap invariant is satisfied. Now we want to poll, so mark the root node red, swap it, remove the 1, and now we would want to bubble down, and the heap invariant is satisfied. Now we want to remove 6, so search for 6 in our tree. Okay, we have found 6, and do the swap, remove 6. Now do we bubble up or bubble down? The answer is neither. The heap invariant is already satisfied, so we don't even need to touch our node. We got lucky. Okay, so from all this polling and removing, we can conclude the following. That polling takes logarithmic time, since we're removing the root and we already know where to find it, and also that removing a random node can take up to linear time, since we have to actually find the index of that node we want to remove before removing it. However, if you're as dissatisfied with this linear removal as I am, you would figure out that there has to be a better way. And indeed there is, and I'm about to show you a hack to improve this complexity to be logarithmic in the general case. So stay tuned. Okay, so now we're going to look at how to remove nodes from a heap with the improved time complexity. To do this, we'll need to make use of a hash table, a data structure I have not yet covered, so buckle up, things are about to get a little wild. I promise I'll cover the hash table thoroughly in a later video, but right now it's going to look like magic. Back to the central issue, we have a bunch of nodes scattered across our heap at some positions, and instead of doing a linear scan to find out where the node we want to remove is, we just want to be able to do a lookup and figure that out. The way we're going to do this is that every node is going to be mapped to the index it's found at.
I know, right? The first time I saw a Steam Deck and it's like 10 fucking buttons and like a guy wonders how much this shitty thing can cost and it's 15K. It's just really overpriced for something that small. It's literally something you can build at home in like, I don't know, well, way cheaper than 15K.
So when we want to remove a particular node, we just look up its index instead of doing a linear scan. Sounds good, right? That sounds great, except for one caveat or two. What about if the heap has multiple nodes with the same value? What problems would that cause? Well, just a few, but nothing we can't handle. To begin with, let's talk about how we can deal with the multiple value problem. So instead of mapping one value to one position, we will map one value to multiple positions. And we can do this by maintaining a set or a tree set of indices for which a particular node value or key, if you want, maps to. Let's look at an example. Okay, so observe the blue heap. Remark that it has repeated values. Namely, we can see that the 2 is there 3 times, 7 is there twice, 11, and 13 once. Below I have drawn the index tree, a tree which can help us determine the index position of a node in the tree. 11, for example, is at index 3, 13 at index 5, and the first 2 at index 0. On the left is the hash table with the key value pairs. Notice that 2 is found in 3 positions, 0, 2, and 6, while 7 is found in 2 positions, 1 and 4, and so on. So this is how we're going to keep track of the positions of the values in the tree. If nodes start moving in the tree, we also need to keep track of that. For example, if a bubble up or a bubble down occurs, we need to track all of those movements and where the swaps go to so we can update the index position in our map. If we swap 13 and the last 7, for example, the following should happen. So we look at where 7 and 13 are in our table, and then I've mapped those respective positions as red for the 7 and yellow for the 13. And this is what happens when we do a swap. We do a swap in the tree, but also in the table. And that's it. Okay, so this all sounds great. We keep track of repeated values by maintaining a set of indices of a particular node, the particular value was found at. But now let's ask a further question. If with the key value pairs, notice that 2 is found in 3 positions, 0, 2, and 6, while 7 is found in 2 positions, 1 and 4, and so on. So this is how we're going to keep track of the positions of the values in the tree. If nodes start moving in the tree, we also need to keep track of that. For example, if a bubble up or a bubble down occurs, we need to track all of those movements and where the swaps go to so we can update the index position in our map. If we swap 13 and the last 7, for example, the following should happen. So we look at where 7 and 13 are in our table, and then I've mapped those respective positions as red for the 7 and yellow for the 13. And this is what happens when we do a swap. We do a swap in the tree, but also in the table. And that's it. Okay, so this all sounds great. We keep track of repeated values by maintaining a set of indices of a particular node, the particular value was found at. But now let's ask a further question. If we want to remove a repeated node in our heap, which node do we remove, and does it matter? Because if we look at our heap right here, there's 3 possible 2 values we could remove. Does it matter which one we remove? The answer is no, it does not matter. As long as, in the end, we satisfy the heap invariant. That's the most important thing. So let's look at an example, not just of removing, but also of adding and pulling elements with this new scheme I just proposed. It's not that hard, trust me. The first one, we want to insert 3. So we need to place 3 at the bottom of the heap in the insertion position. We also need to track where the new node is, so we add 3 to our table, along with its position, which happens to be at index 7. Look at the index tree in gray to confirm this. Now that 3 has been inserted, we need to make sure the heap invariant is satisfying. Currently, it is not. So what we do is we bubble up 3. The parent of 3 is 11, which is greater than 3, so we need to swap those 2 nodes. I've highlighted the 7 in the index tree because it maps to 3 in the heap, and 3 in the index tree because it maps to the value 11. Now swap those both in the tree and in the table. Awesome. Now the heap variant is still not satisfied, so do a similar thing for the node above. We grab the parent and do a swap in the tree and the table. And now the heap invariant is satisfied, so 3 has been inserted successfully. The next instruction is to remove 2 from the heap. So which two should we remove? Well, as I said, it doesn't matter as long as we satisfy the heap invariant in the end. If we remove the last two, we can immediately satisfy the heap invariant with one swap. But for learning purposes, I'll simply remove the first one found in our set, which happens to be located at index 0. So we want to remove the two at position 0. So how do we remove a node again? So we did a lookup, so we didn't have to do that linear scan, which was nice. And now we swap it with the last node, which happens to be 11. We remove the last node. Now we need to satisfy the heap invariant. So we need to bubble down 11. So we look at 11's children, which happens to be 3 and 2. 2 is smaller, so it's the one we're going to swap with. So swap it in the table and in the tree. Now we are still not in satisfaction of the heap invariant, so look at 11's children being 13 and 2. 2 is smaller, so swap it with 2. And that's it, we're done. The last instruction says to poll, so get the value of the root, which is 2, and swap it with 11. Get rid of the 2, and bubble down 11. So as you can see, we're constantly updating our table, but still doing the same operations. So that's how you do quick removals in a priority queue. Alright, welcome back everybody. This is part 5 of 5 in the priority queue series, and we're going to have a look at some source code for the priority queue today. So if you want the source code, here's a GitHub link with all the data structures in the series. The priority queue is one of them. Also make sure you've watched parts 1 to 4 so you can actually understand what's going on. Alright, let's dive into the code. Alright, here we are inside the source code. So notice that inside my priority queue, the types of elements I'm allowing inside my priority queue have to be comparable elements, as we talked about. So if they implement the comparable interface, then we are going to allow them inside our queue. So this is anything like strings, integers, anything with a comparable interface. So let's have a look at some of the instance variables. So I have the heap size. So this is the number of elements currently inside the heap. But then I also have another instance variable, which is the heap capacity. So this is going to be the size of the list that we have for our elements, which may be larger than the heap size is. And this is the actual heap, and we're going to be maintaining it as a dynamic list of elements using Java's list. Next, for our log of n removals, I'm also going to keep track of this map. And it's going to map an element to a tree set of integers. So these are going to be all the positions inside our heap, which we can find this element t. Alright. Next, I've got a few different constructors for our priority queue. We can just create a priority queue, and by default, I'm creating an initially empty priority queue with a capacity of 1. But I also allow you to create a priority queue with a defined initial capacity, which actually is more useful, because then we don't have to keep expanding our dynamic list every time. So I would recommend this. But also, even better, is if you know all the elements that are going to be inside your heap, you can actually construct the priority queue in linear time using an operation called heapify, which I didn't talk about in the slides, but it can be very, very useful. So this just has all the usual setup stuff. Here I'm adding all the elements to the map, but also to the heap. And then here's the heapify process. So we start at about halfway through the heap size, and then we start decreasing, and then we sync all the elements. And you're like, wait a second, isn't the sync a logarithmic removal? Well, yes, it is in the general case, but all the elements. And you're like, wait a second, isn't the seek at adding all the elements to the map, but also to the heap, and then here's the heapify process. So we start at about halfway through the heap size, and then we start decreasing, and then we sync all the elements. And you're like, wait a second, isn't the seek sync about halfway through the heap size, and then we start decreasing, and then we sync all the elements. And you're like, wait a second, isn't the seek sync a logarithmic removal? Well, yes, it is in the general case, but not if we're doing it in this fashion. I put a link to this paper up here just because the heapify operation isn't quite intuitive why it has this linear complexity. And if you look at the analysis in the paper, you'll end up seeing that the complexity boils down to a convergent series, and that's why we get a constant in Kincaid's linear time. But in general, this isn't what you might be tempted to do if you're giving a collection of elements. You would initialize the heap, and then you would just use our add method to add the elements one at a time. And this will give you an n log n bound, but definitely use the heapify whenever possible. Okay, now some pretty fine. And this will give you an n log n bound. Collection of elements, that's why we get a constant in Kincaid's linear time. But in general, this isn't what you might be tempted to do if you're giving a collection of elements. You would initialize the heap, and then you would just use our add method to add the elements one at a time. You might be tempted to do if you're giving a collection of elements. You would initialize the heap, and then you would just use our add method to add the elements one at a time. And this will give you an n log n bound. But definitely use the heapify whenever possible. Okay, now some pretty simple methods possible. Okay, now some pretty simple methods. We have is empty, just returns true or false if the heap is empty or not. Then clear. So when we clear the heap, we remove all the elements inside our heap array, but also inside our map. So that's why I call map useful method just looks at the top of our size heap and return it. Similar to peek, except that we're going to add where next contains. So because we look up to see if linear, in which case we have constant time, which is the maintained possible. Although the map does add a lot of constant. Personally find that the overhead is quite a lot, and I usually don't really remove things very frequently from maps, so it might not be entirely worth it. But it's up to you. If you're doing as many additions as you are removals, then definitely worth it. Alright, now let's have a look at the add method. Uh, so, so this element, this method adds an element to the priority queue, and that element cannot be null. So what we do is, first we check if our heap size is less than capacity. Otherwise, what we do is first element to the priority queue, and that element cannot be null. So what we do is, first we check if our heap size is less than capacity. Otherwise, we have to expand our capacity of the heap. Next, we make sure we add it to the map so we keep track of it, and then we swim it up. Remember that we have to swim a node up because we add it to the very end of our list, and so we have to adjust where it goes inside our heap by swimming upwards. This next method called less is a helper method which helps me check if node I is less than or equal to node j, and this uses the fact that both elements, node 1 and node 2, are comparable, so we can invoke the which we needed. So let's scroll back down. Alright. So it returns true if I swim. So we are going to try to swim node k. So first we grab the parent of node k, and we can do that by solving for the parent. So remember that I'm working in, I'm starting at 0. Some people like to start their heaps indexed at 1. I like everything 0 based. So I get the parent, which is at this position, k minus 1 divided by 2, because we're going upwards. And while k is still greater than 0, so we're not at the root, and we are less than our parent, then we want to swim upwards. So we're going to swap the nodes, parent and k, and then k is going to become the new parent. And then we have to get the parent of k once more. And then we keep doing this, going up our heap and swapping nodes. So that's how we do the swim. So the sync is similar, but a little different. So this is a top-down node sync. So the sync is similar, but a little different. And swapping nodes. So that's how we do the swim. So the sync is similar, but a little different. So this is a top-down node sync. And here we want to sync node k. And what we do is I grab the left node, but I also grab the right node. Remember, we're working 0 based, so +1, +2 instead of +0 and +1. And then I need to figure out which is less. Either it's going to be the left one or the right one. And I assume to start with that the left one is going to be smaller than the right one. And here I correct that hypothesis in case it was false. So I check that the right node is within the size of the heap, and if the right node is less than the left node, then the smallest one is going to be the right node. And our stopping condition is that we are outside the bounds of the tree, or we can't sync any more. a similar thing. We swap, and then k is the next smallest, kind of like we did in the last method also. So the swap method, I made an explicit method to swap because I also have to swap things inside the map and then set the values also. And this is really what adds a lot of overhead for the map. It can be a lot of hashing, and technically maps are constant lookup times, but the fact that you're doing all this internal hashing and collisions and whatnot, it can get costly. So remove. So if the element is null, return false. We know we don't have any null elements inside our heap. So this is how you would do a linear removal in linear time. I commented out in case you want to revert back and remove the map and whatnot. Is you would scan through all the elements, and once you find the element you were looking for, just remove it at that index and return true. Otherwise, we're going to use our map. So get the index of wherever the element, one of the elements are, and if it exists, then remove it at that index. Okay, now let's have a look at the remove at method. Heap is empty. Well, of what then? Remove check whether if nothing happened, then I try swimming downwards. So if it so happened that I was equal to the heap size, meaning we just removed the. So if it so happened that I'm going to swap the index of what we want to remove with the last element, which is going to be at heap size. And then we're going to kill off that node and also remove it from our map. So if it so happened that I was equal to the heap size, meaning we just removed the very last element in our heap, just return the removed data. Otherwise, when we did the swap, we have to either sync that node up or down. And I'm kind of too lazy to check whether I need to sync or swim, so I just try both. So first I try syncing, and then if nothing happened, then I try swimming downwards. And in either case, return the removed data. Perfect. So this just readjusts where the swap node position goes, either bubble up or bubble down. This method is just a method I use in my testing framework to make sure everything is good. So it checks essentially the integrity of the minimum heap. So initially you call this method with k equals 0, and that starts at the root. And if so, we're just going to return true. Otherwise, get our children left and right. And now we're going to make sure that k is less than both our children. And if that's not the case, return false. And if we ever return false, because we have an and statement when we're recursing right here, that gets propagated throughout the recursion, and this whole method will return false. Otherwise, if everything returns true and hits the base case, then we know for sure it's in the minimum heap. Okay, these last few methods are just map helper methods, so things to add things into the map, how to remove elements from the map, and so on. And what I'm doing here is I'm using a tree set to add and remove elements, because I know the tree set implementation in Java is a balanced binary search tree, so all operations on tree sets are logarithmic, which is really nice. So you guys can have a look at those in more detail. It just gets values, removes values, and lastly, do a map swap. So yeah, it swaps values in the heap, or in the map rather. So you guys can have a look at those in more detail. But I pretty much covered everything about the priority queue. So if something's unclear, just drop a comment and I'll get back to you as soon as possible. But that's the heap, the binary heap implementation of a priority queue. Remember that the source code is on my GitHub repo, so you can have a look at that. So guys, thank you for watching, and I'll catch you next time. Alright, time to talk about the union find, also sometimes called.
Right. This was just as boring as a lecture should be. And union find. What's this guy sending me? Anyways, right, like I was saying. Oh, I also tried doing this problem because, well, just because Not really anything. No real insights right here. Introduction to priorities on using binary heaps. Priorities in binary heaps, binary trees, binary heaps. No, he's right. Try it on GOG practice. Right, min heap. And I solved it already. Min heap if I. Oh, my ass hurts on this chair, bro. It's not even a joke at this point. It's a complete tree all over the field. Binary heap is a min heap max heap. In a min heap, here the root must be minimum. Because it is true. You're given an empty binary min heap, and you're supposed to do what? Implement three methods: insert key, delete key, and extract min on the binary min heap, and call them as per the given below. Insert key, delete key, and extract. Three methods. Function to change values of the ith index and store the value at first index. So, wait. Structure the classes struct min heap. Same property as your a query this type means. Right. This is the structure. H heap array. Okay. Capacity, heap size, min heap, and cap. Capacity to cap, event, extract min, void delete key, right. Delete key, insert key, decrease heap file. In above codes, please do not delete this code if you are not writing your own min heap file. L equal to left, I, R equal to right, I. What the fuck? What? And left and right. Okay, it's already implemented. I hope it is. I hope it is. In smallest equal to I. What? If L is less than user, HR sound is equal to L. If right is less than user, then right is less than smallest equal to R. Smallest is not equal to I. Well, what if? Okay, yeah, okay. Swap I, the smallest one. So basically, it takes the left and the right of the heap, finds the smallest, and swaps your parent element with that element. Min heapify smallest, and then it does this recursively. Okay, I got it. This is a function to change the value at ith index and store that value at first index. I equal to new val, got it. is not equal to 0. Parent I is greater than I swap. I have no idea. What? So basically, it takes the index I, change the value at I, and store the value at the first index. And then I is not equal to 0. And if the parent of I is greater than the element, then swaps it with its parent, and then I is equal to parent of I. So it's basically a bubbling up function, a swing function. This is just a heapify function. So what I need to do is I need to extract the min for 2, 6 to 8 key. Min element from heap 2 and from Z. Okay, so it also needs to remove the element. So int min equal to is there a swap function? No. Gotta do that shit on my own. So you have the zeroth element and the last element, and then delete key. Delete element at position 0 of the heap. Right. This is the same function, so it's maybe for 0. Got it. Okay, and then now I have to implement the delete key function. So to delete a key, I need to swap it. Or reduce the size to and then stream and when I don't know. It hasn't even been an hour, and I need to do at least some questions. So you swap the last element with the index -1. Once you've swapped both of them, what you need to do is remove the last element. So that's how am I supposed to remove the last element then? Well, all you have to do truly is heap underscore size minus minus, and then then you can assume the value is deleted because you can't ever access it, right? So once you decrease the size, you need to sink or swim. Right. Heapify. It's just a very bad way of implementing the data structure, honestly. I want to do this in C++ by scratch. Sudo min heapify I if I if it's not even heap, it's called HARR min heapify I if heap array I. Wait, so what's it supposed to be like again? You swap these, you decrease the size by 1, and then you min heapify I if HARR I is equal to, I want to check if it's still the same. All right. Is still the same. Man, I'm just gonna int temp if it's equal to temp, then decrease key I. Void min heap insert key. So do this equal to k, and then you min heap for this. Is that it? He was not declared in this. Okay, swap. Where do I swap? Expected comma. It was from 5 where 107. I got this. This is such a bad color for this website, bro. Can't hear. I've got 49 in my. Somehow I've got 49 in my heap. Such a bad way. And I am sleepy, bro. It's 12. No, well, no fucking wonder I'm sleepy. Um, okay, I just wanna look at this solution because then I have done at least 2 questions for today. I'm fine with that. Incorrect starting on logic. Wait, so start is 0, max length is 0, and equal to 0, and is less than s dot size, n plus plus, s n plus plus, greater than 1, start plus plus, max length to max length, and minus start plus 1. Got it. I'm gonna attempt it again tomorrow. Basically a for loop at the end, not declaring it in another loop. Excellent. Ah, that was way more simpler. Right, I'm gonna go sleep. I feel really sleepy. I'll have to do streams in the evening, not at night. I get too fucking sleepy and then none of this shit works out like it should. Although I do practice DSA in the morning too, and I planned on solving a contest for today. But I woke up around 8:30 and the contest was at 8. And then I proceeded to fuck around for a while, make breakfast and shit. And by the time I open LeetCode again, not even again, for the first time, I look at the discussion and there's like LeetCode contest is live 36 minutes ago. I'm like, fuck, missed that. But well, I'll try and not miss other contests and I'm gonna go sleep, bro. I'll go sleep. If you guys are still tuned in, maybe you should go sleep too. Right? Thanks for tuning in. I'll see you guys tomorrow. Bye bye.